Hello everyone, and welcome to this third episode of our Zetta Platform webinar. Today, I'm pleased to have with us Salva Rodríguez, which is Head of Product Management at TTTech Auto. And you are becoming now almost a regular on our webinar. It's always a pleasure to have you on. I'll let you quickly introduce before we get going with the slides.
Great, thank you, Angelo. It's always a pleasure to host those webinars with you. So my name is Salvador Rodríguez. I'm the head of product management at TTTech Auto. And yeah, we have been working together with Angelo and the team in something special that we want to tell you about today.
Okay, great. So I would say let's get started. So I'll be sharing my screen and we'll be both presenting. I'll be setting a bit the stage and then Salva will go into the details of Zetta Auto. Actually, let me go back here. Oh, here we go. So you should be able to see my screen in a matter of seconds if you're not already seeing it. So I'll give you just a little bit, few seconds to make sure that we are all there. And I believe we are, so let's go. So today's webinar is about Zetta Auto. As we announced on the 6th of July, this is a verticalization of the Zetta platform addressing automotive. And we'll tell you everything about it in this webinar. But before getting into, let's say, the area that will be our primary focus with the first release of the Zetta Auto platform, which is the on-vehicle solution, I would like to go back for a moment and see what are the challenges that we are solving overall with the Zetta platform so that you will have a big picture of the capability and the features that we are bringing to automotive, okay? So to begin with, now, one of the problems that we have witnessed, and this is a problem suffered in several different industries, is that of the integration Frankenstein. Right? This is true for robots, it's true for vehicles, it's true for general IoT application. But in general, today, the system that we are building are spanning from the microcontroller up to the data center. So in a car, you have from the MCU up to the cloud, potentially. But it's the same in robots, it's the same in domotic application, and so on and so forth. And the challenge that exists today is that in order to build these systems, even if we only consider the aspect of data in movement, so trying to ship data around our system, that require us to integrate 2, if not 3 different technology, which is quite painful. And then if you look into data storage, again, that gets additionally or introduces additional complication because as soon as data is stored, we lose location transparency, and all of a sudden that we need to know where is stored the data physically, or the location of that storage, and as all of this pushes us toward a cloud-centric architecture that, as we will see, are not always possible depending on use case, and some of these use cases are quite central in next-generation automotive, as I will describe next. And last but not the least, let's not forget that in a distributed system, right, we have information flowing, we are storing information, but why? Well, because we want to perform computations on that information, on that data. And so usually you need yet another framework, that is different from the framework used to distribute the data, from the framework that used to retrieve the data to do computation. And that's very cumbersome. That leads to architecture and system that looks a little bit like this, or sometimes uglier, rarely more beautiful than that. And the question is, how can we address these challenges? So as you know, as individuals and as a company, we've been involved with DDS since the very beginning. I was one of the 3 amigos that started the DDS standardization or the DDS standardization group back in early 2000. We have been involved with protocol for most of our life since I was, I would say, a kid. I was always passionate by this topic. And what we realized at some point is that while DDS is great in addressing certain class of problem, if you look at the system we're trying to build today, it falls short in some dimension, right? And so we needed to move next. And in the past several years, as perhaps you have now learned, we started working on a protocol and says, okay, if we were to design a protocol to address this problem end to end, what would we do? And we came out with Zenoh, which is the first and only protocol today that is able to support you for data in motion, so pub-sub from the microcontroller to the data center, a query, distributed query, and it's data-centric, so you don't need to know where the storage are. And as we have explained in previous webinar, you can integrate your favorite storage from InfluxDB to RocksDB, Amazon S3, Minix, file system, and memory, whatever. but also able to represent distributed computation, as we will show. And so it gives you with the 3 key universal abstraction for building distributed system in a very efficient end-to-end protocol, a protocol that, as you have come to learn, has an overhead of roughly 5 bytes. Now, obviously, automotive is a safety critical market. All safety critical markets are quite conservative in technology adoption, but I would say that we have today already good sign of adoption of Zenoh in automotive. Zenoh has already been adopted in domains such as transportation on railways, and its mainstream technology for robotics. And one of the reasons why, in spite of its young age, it has been so successful, I think, can be summarized in some of the quotes that, by the way, you can see with your eyes in our Discord channels, and I will let you read, right? So I think this is one of the key elements. But again, companies like Amazon have been considering Zenoh as the protocol for solving the problems faced when trying to build IoT systems. As you will see in this article published by Richard Elderberg in January earlier this year, he identified Zenoh potentially as the protocol that addresses all the challenges that aren't addressed by protocol available today, like MQTT, NQP, DDS-Scope, because those protocols were designed at best 20 years ago, if not earlier. But again, what are some of the challenges? I want to share one with you that is precisely addressing automotive market, and was the reason why the ITU went through advocating or recommending Zenoh as the standard for intelligent transport communication. So the use case that they had was that of a digital witness. Imagine in the future 2 autonomous vehicles crash into each other. If you think about next generation cars, we usually say that they are, a data center on wheels, which is kind of true. So you will have inside the cars, obviously, a reconstruction of the environment. You will have cars that were close to the car in which that crash happened that will also have a reconstruction of the environment. And part of this information might be shared with some infrastructural node, but for sure, not all of that information can be stored somewhere on the cloud. It's just not possible, because it would take too much energy, it would take too much time. I mean, it just doesn't make sense. And so the question is, when a crash happens, okay, how do you know who was wrong? Because machines don't lie. And so the reconstruction that you have in the 2 cars is high fidelity with respect to what they thought was happening or was around them. So you will need to benchmark this with the view of cars that were close by. But those are database on wheels. How are we going to query those? We don't know their location, right? So as you will see, this is one of the problems that we solve with our Zetta platform, and some of the feature that you will be able to tap in adopting Zetta Auto. Okay, let me just go quickly here. So in terms of protocol, Zenoh runs everywhere. And by the way, one of the limitations that we were struggling with in DDS was scaling down. And so running either on very constrained network or very constrained hardware. And of course, there was, and those of you that know me well, there was a standard initiative called XRC that from my perspective ended completely in the wrong direction, because the protocol that was standardized, as we will see, is very inefficient, extremely verbose, and doesn't standardize any API, doesn't support QoS, and is not interoperable with DDS, as we will see. Okay, so it's not a single protocol really that allows you to go from a GPU or a general purpose processing unit to a microcontroller. You are bridging into a protocol that actually, I suggest you look at it, isn't very efficient. But anyway, so Zenoh was designed to be very efficient and to squeeze out any extra data that is not required. So as such, is able to run on top of a data link, but as well as transport and network, so in between. As of today, we have transport for UDP, TCP, quick serial, Bluetooth, open thread, Unix socket, share memory, you name it, okay? And again, the wire overhead is only 5 bytes. And our embedded version runs, wrong order. So our embedded version runs on pretty much anything you can imagine. The bulk of the code is developed in Rust. Rust is becoming more and more important in automotive because of the safety implication of this language and the security implication of this language. And in terms of topology, Zenoh doesn't pose you any constraints, okay? So you can run, again, peer-to-peer, you can have brokered, you can have clients that peer up with peers, you can support mesh, and so on and so forth. So talking about constrained environment, it runs on Arduino, it runs on Embed, it runs on Zephyr, it runs on FreeRTOS, it runs bare metal, essentially it runs wherever you want. And we have some deployment on super constrained oceanographic drones, where you have incredible constraint in terms of resource usage, because as you can imagine, anything that has to do with ocean, with high pressure and salt, has to be extremely high quality. And so you have to lower the computational power of those platforms and the bandwidth, because otherwise the cost gets completely, off the roof. In terms of performance, it's the technology based on third-party evaluation. This is an evaluation from NTU that is available on our, as a contributed blog on our website. It performs better than anything else out there, both in terms of throughput and latency, and it's extensible. And I want to pause here because one of the nice things of Zenoh and the Zetta platform is that provides you with integration with many other protocols, most of the mainstream, MQTT, DDS, OPC UA, and so on and so forth. DDS, as we are a DDS vendor, we have a super efficient integration with DDS that leverages a zero copy, and I'll explain that in a moment. And besides the integration with the protocol, we have also various integration with the database and backends. So now we spoke about the integration problem. We spoke about a protocol that can help you glue everything from the data center down to the microcontroller. So why do we need Zetta? Well, the issue is that if you're building a system that scales from the microcontroller, your MCU, up to the data center, you will need some routing infrastructure, and I mean soft router. By the way, I will address this later, but today, most of the V2X or V2 infrastructure in automotive is done with MQTT. And you know better than I do that that's creating problem in terms of scalability, in terms of throughput. And as soon as you will try to have some form of edge computation, where will you put the broker? Okay, that doesn't work. But you have a topological limitation that is imposed over you by MQTT. In Zenoh, you don't have such a topological limitation, and so you will be able to deploy a graph-of router, potentially across the globe. But then the question is, who manages those routers? Where do you deploy those routers? And this is the question that answers, among other, the Zetta platform. So Zetta leverages Zenoh to unify communication, storage, and computation from the cloud to the microcontroller. But again, it provides you with a cloud-independent infrastructure that can work on AWS, Azure, Linode, as well as on-premises, okay? As we will see, we can deploy, and as we demonstrated at our previous webinar, we can deploy from the data center down to the device. And if you go and look the webinar we did last week, we were showing deploying precise infrastructure down to a robot, okay, that then we were teleoperating. And again, this is important because, once again, if I take the example of MQTT, if you use MQTT to communicate with, to do V2X, all of a sudden, in spite of two applications being close to each other, perhaps on the same network, they will have to go through the cloud to communicate. That's not good in terms of latency, it's not good in terms of energy utilization, but more importantly, it's not good in terms of OpEx, because recall, anything that gets on the cloud, it's built, okay? And if that information is getting to the cloud only to get to the device that is close by, you are just burning money, okay? And with using our technology, you will be able to deploy routers on-prem and ensure that any communication that can be retained locally will remain local. That will cut down incredibly your OpEx. And anything that needs to be shared beyond that scope, obviously, will be routed by Zenoh. So once again, our infrastructure can scale and be provisioned from the data center down to your device, passing to any kind of edge. Why do I say edge? Because, for instance, in robotics, we have already deployment in which we have some infrastructure running on a cloud, private or public. Some infrastructure, in fact, Zenoh is already integrated with the core network of some 5G providers. So you have Zenoh routers that are running in combination with the 5G access point, okay? And then you have the 5G devices that communicate between them within a factory or perhaps across factory using this infrastructure. But again, the advantage is that from a single and central point, you can provision a secure end-to-end infrastructure. So in terms of the Zetta platform, you have the bus, Okay, so the platform as a service, you have our router, and the router, once you define your system, you can generate routers that are already configured for security that include all the required plugin that can be then provisioned on premises. You have all the series of connectors, tools for monitoring, and API in your favorite programming languages. A special connector, as I mentioned before, is DDS, and I'll get there in a moment, right? But then we have connectors also for third-party technology. For us, DDS is special because, as you know, we are a DDS vendor, so for us, it's a first-class citizen in the Zetta platform. Talking about DDS, obviously, our DDS solution in the Zetta platform and as such in Zetta Auto is based on Eclipse Cyclone DDS, which, like Zenoh, is an Eclipse open source project that we lead within the Eclipse consortium. This is, from my perspective, like the Nespresso for DDS. When you think DDS, it's like, what else? Why? Because it's fully open source. We redesigned it from scratch. We have an older DDS implementation that has been around 20 years. Cyclone was redesigned from scratch. And actually, we were pretty smart on how we did it because we started from the core, and we started replacing the core, in fact, the communication stack, on our older products so that we could get hour of deployment. So the result of this is that you have a stack that is essentially rewritten, clean code, incredible performance. It has been proven in some of the most complex distributed systems. If you look at some of the assessment done, for instance, by a company like Trend Micro, is the most secure. And then if you look, for instance, at what is happening in robotics, most of the people in the real world deployment use Cyclone because in real environment is the one that deliver the right performance. And then there is a combination of Cyclone and Zenoh that interoperate smoothly and high performance that, again, in robotics makes it very easy to do R2X, either for robot-to-robot communication across arbitrary network or perhaps teleoperation. And so if you make a parallel, what we have been doing in robotics, it's quite similar to what next generation automotive will have to do. And thus, the verticalization that we have started of this platform toward automotive. So let me look in some automotive use cases. Salva will be covering, in fact, the on-vehicle platform because this is the first stack that we are releasing. That's what we are focusing on. But by the way, if you want to leverage the V2X, the Zetta Auto is fully interoperable with the overall Zetta platform, so you already can. But this is what we are focusing to begin with. And again, support, as we will see, for AUTOSAR Classic, infotainment, and certified ISO 26262 ASIL-D. But this is the part that will be zoomed in by Salva in a couple of minutes. So let's focus with me on off-vehicle. So today, as I mentioned before, how is the automotive industry dealing with off-vehicle communication? Well, they are doing MQTT. And MQTT provides you with a publish-subscribe abstraction, which is powerful. But then it forces you into a topology that has nothing to do with PubSub. PubSub is a concept, is an abstraction. And the fact that MQTT takes an hub-and-spoke architecture to implement a PubSub abstraction is just an arbitrary choice. But this choice that the architect of MQTT made is being forced on you. And as a consequence, you have the problem of where do you deploy this broker? The result is that most of the time you have to deploy the broker on the cloud, which means latency. Again, it means energy, because let's not forget that in order to reach the cloud, the problem is not just the energy used by the data center and the energy used by the end device, it's the energy that is burned by all the routers that are in between, running for thousands of kilometers between your car and the data center where this broker is deployed. And based on what we have seen previously in robotics and more in automotive, there is a pain point. I mean, there are a few pain points. Pain points are related to scalability because these architectures are to scale. The only solution is to scale up, right? Use bigger server or use proprietary solutions to scale out the MQTT broker. So you get into completely proprietary solution, you get completely locked in. What is the other solution? Well, the other solution is that if you adopt Zenoh without changing anything in your system today, right, you can still believe or let your application communicate through MQTT, but all of a sudden you can deploy the MQTT routers anywhere on the network as Zenoh plugin And it's the Zenoh protocol that will allow you to route between those brokers, okay? So now you can scale out. Now you can bring the router closer to where the production of the data is, and thus reduce latency, facilitate some form of edge computing. And on top of that, in our platform, any of the protocol that we support as a plugin is interoperable with native Zenoh application and with any other protocol supported. So what this would allow you is to have application that publish on MQTT and subscribe to data in Zenoh or DDS, or vice versa, or perhaps any other of the supported technology. So this is, I think, very powerful, because all of a sudden there is a pain point, right? And just by changing the underlying backbone and making it Zenoh-based, you're solving the problem that you have today and opening the door to a series of innovation that can come later that I'll mention in a moment. So talking about the new possibilities, what are the new possibilities that the Zetta platform opens and brings to automotive? So imagine in the near future, right, we will have 5G sufficiently deployed, because again, the 5G that we have deployed today is mostly the physical layer between your mobile and the antenna, but the core network in most countries still a 4G core network. So there aren't many MEC server on the edge that you can leverage, but this will become either with 5 or 6G, which by the way we are working on. So most of the 5G core network we are seeing as of today deployed in private environment as opposed that in public. But again, if you are a car manufacturer, perhaps you will roll out your own 5G infrastructure. That's also a possibility, right? Anyway, so imagine you have this scenario and we have our infrastructure deployed again from the data center down to the device. This will allow peer-to-peer communication, potentially V2V communication, as well as V2X with the same protocol, right? And you will be able to support the topology that makes the most sense. Not only, we have support for disconnected devices. So if you have devices that sleep because of battery constraints or because they are sporadically connected, the infrastructure can keep data around, and then this device, as you see in the animation, can consume the data at their pace, okay? But more importantly, if we go back to the example that I was giving on the digital witness, how can you solve problems that are the digital witness or like the digital witness, in which you need to query a data set, right? But you don't know where the storages are. Well, as with Zenoh, we are able to transform data storage in a network endpoint that are location transparent. In Zenoh, you can just issue a query, and it's the Zenoh protocol, right, that will be able to go and fetch this data, even if, by the way, the data was perhaps produced by DDS or MQTT. That's powerful, right? Because all of a sudden, the advantages that our backbone provides are enjoyed by all the other protocol that we integrate with. Once again, with DDS being one of the first class integration. So the one where we have, we can play more trick because we implement both technology. So in this case, you do a distributed query, and without knowing where the data is stored, just because you were on that part of the network, our protocol decides that those cars are the entity that have the data you're interested in, and you get the data back. But suppose you move, or some other operator on the other side of the network issues the same query. Perhaps in that case, the closest storage that contains that information is in a data center, okay? And perhaps that's how you get the data. So this is quite powerful because it means that wherever you are on the network, you're able to get the data that you're interested in from the optimal set of storages. And you don't need to know where the storages are. This is very powerful. It's very powerful because it brings location transparency to that address. But how about computation? Suppose that now I have a car that perhaps wants to offload some ADAS computation to a service. How do you know to which service? And how do you load balance? How do you do fault tolerance? Well, once again, as with our platform, we have location transparency also for computation. You will just try to resolve a resource. It will be routed to the closest computation. The computation will be triggered. You have the result. If the car moves, the same request potentially might be routed to another computation, okay, that obviously provides the same service, completely transparently, and you don't have to do anything special, okay? So that's because of the data-centric nature of the protocol. So you can understand that this can bring quite incredible a platform for innovation and for next generation automotive. But I think, hopefully with this excitement in mind, then now let's go back and let's focus on the on-vehicle platform. And I will let Salva take us through what you can start using as of today with our on-vehicle platform for Zetta Auto. So let me stop the sharing, and the floor will be yours, Salva. Here we go.
Thank you, Angelo. Let me know when you will be able to start seeing the deck.
I can see your slides. We are good to go.
Great. Perfect. So thank you for your introduction, and thank you for introduction towards the overall Zetta platform. And now we go a little bit more in detail about automotive. What does it mean for automotive? A couple of months ago, approximately, we were talking about where we had our first webinar, right? And we were talking about why DDS in automotive. What about service-oriented architectures in automotive? And what is the challenge in automotive? First of all, I would like to step back and recap on those items. So on TTTech Auto and us, basically, we took the challenge of making service-oriented architectures possible. So today, we see service-oriented architectures an imperative, mainly because enable us to have a higher abstraction between application and hardware, and as well enables the collaboration, enables scale-up development if we compare it with the past of development cycles in automotive. But what we have been seeing and identifying in the last years is that nobody is able to give the proper balance between flexibility as well as determinism. So we need to be flexible during development, but we need to be able at a certain point of time to freeze and to be deterministic as soon as we are about to go into the vehicle. And this is what we are doing. We are doing together with ZettaScale team, and that is what is Zetta Auto based on. So first of all, just to give a quick recap. First of all, Zetta Auto is a new branding name. Before, in the first webinar as well, in our communication, we have been referring to it as a motion wide cyclone DDS. The first thing is what we want to make clear: motion wide cyclone DDS now becomes Zetta Auto, and Zetta Auto is the joint product that ZettaScale and TTTech Auto is working on. Important is, as Angelo has mentioned, so it's based on open source technologies. It's based on DDS as a foundation, as well as Zenoh for certain aspects that we will talk about it. We're talking about how do we exploit Zenoh Pico for the microcontroller area. This is one of the aspects that we have identified, but also how do we leverage Zenoh in general to provide a continuum view in terms of in-vehicle technology with cloud. So at the end, our major goal is to, first of all, to fix the challenge of service-oriented architectures in automotive, to help OEMs and automakers on meeting SOP timelines. This is something that we were discussing in the previous webinar. We need to help them in all the hurdle of managing complexity. And as a second step, what we will do is to conquer the communication between the edge and the cloud. And during my presentation, we'll go a little bit more in detail about how does it look like from the software layer, and as well how does it look like in terms of the product. What is the product composed from? So, as I mentioned before, DDS is the foundation of Zetta Auto. We bet on DDS because we believe that it's a more promising technology than any other technology that is out there. And DDS will be deployed in microprocessors. We'll have as well the version for the microcontrollers that we use Zenoh for it. An important aspect is we will exploit time-sensitive networking in order to provide deterministic behaviors in the area of communication. And this is critical in order to be able to solve the integration problem and to enable our customers, and our customers are car makers and OEM, on facilitating or easing the efforts and the investment that they have to do in integration, validation, and verification. And this is mandatory. So we need to have a proper trade-off between flexibility and a proper trade-off between flexibility towards determinism. And this is what we are doing by having a professional edition or having a Zetta Auto, let's call it Pro edition, that it has a broader feature set, and that feature set is one-to-one to the DDS feature set, so we can have much more dynamic behaviors, and as well we can transition towards the certified version in a matter of a click, and have fixed behaviors that are ready for your safety critical / real-time applications in automotive. As I mentioned before, as well, it's not only about safety. We'll have ASIL-D early 2024. We are working on that. It's about having a performance behavior. So today, the vast majority of problems that we are facing, or the automotive industry is facing, is the non-performant communication stacks. So quite a lot of problems are coming due to those non-performance communication stacks, and that's why we are, one of our utmost interests is to have an extreme performant communication that it blends software together with hardware, and as well with the communication layer in the area of TSN. And we would like to provide it as a safety element out of context, enabling our customers to integrate it by themselves and standardize, as well as commercial operating systems, like it can be QNX as an example. You can see here already some of our third-party stacks that we are working on, having adaptive AUTOSAR, having classic AUTOSAR, having QNX, having Linux for the professional edition, as well as it will be fully integrated in TTTech Auto motion-wise safety mode. When we make a double click about how architectures are looking like, here you can have is an overview overall of how an architecture in automotive is looking like. So today we are taking a look we are in the transition from distributed architectures to domain controllers, zonal architectures, and pretty common what we can see is a microprocessor that it contains a POSIX-based operating system, and then DDS, what enable us is not only to have a communication mean, but to provide an API towards the users in order to enable to code their applications according to the DDS API standard. This is one of the benefits that we have if we compare it with another ones, like it can be some IP. That some IP is below the hood of overall adaptive AUTOSAR and ARACOM API. That one, it doesn't mean that only DDS is the API to be used. As well, we do have an integration with adaptive AUTOSAR. So for those that are using adaptive AUTOSAR, they can exploit DDS and they can code their applications according to an ARACOM specification. And as well, an interesting aspect that we are working on is on how do we harden Zetta Auto, in this case with ROS2. So at the end, we are taking out all the fat that we are having and to have a performance integration of ROS2 together with Zetta Auto platform, in this case, starting with DDS. An important thing is what we have been mentioned, and Angelo mentioned, is the aspect of cloud. So we want to go beyond the edge. We want to break with the chassis and reach the cloud. And that is something that enables us exploiting Zenoh as an overall technology to have that continuum view between the edge to the cloud. Everything will be fully integrated and fully transparent towards the users. A pretty similar view, but now I wanted to talk about networking. So we have seen, and we on the recent years and the past years, the topic of DDS together with TSN. I will talk a little bit later, but this is extremely important once that we are talking about end-to-end communication. So in communication, we have two aspects. We have the communication that it happens within the same chip. And for that one, we are working a high performance, safe shared memory communication layer in order to be able to exploit the communication between applications happening in the same SOC. But as soon as we go towards communication between different devices, either between different SoCs or between different ECUs in a full EE network, what we are doing is to exploit TSN. And we exploit TSN in order to obtain deterministic behaviors. So we shall not forget that automotive is, we are leveraging software, and we are today living a revolution of software. But we shall not forget that at the end, eventually it's a vehicle that it needs to be controlled. It needs to be controlled with hard real times pretty often. And we need to have an end-to-end profiling, let me call it in that way, of the overall communication. So at the end, we cannot live with having such kind of behaviors. Otherwise, all of us, we know what it might happen. But at the same point of time, we need to be flexible. So at the end, we are merging all those different properties, flexibility, in order to enable that higher level of abstraction, in order to enable a vast number of application developers to work in a parallel mode, but also to provide that smooth transition towards a mass production system with everything safe, deterministic, etc., etc. And for that one, we exploit those technologies. We exploit DDS, we exploit TSN, and as well we are exploiting Zenoh. First of all, Zenoh Pico, and we'll go, as I mentioned, towards the cloud. Here you have a little bit more into details. How is that overall stack looking like, and as well as some of the characteristics that we are working on. This is the view of Zetta Auto. Then next we'll go towards the view of the certified edition. So we are working in C, C++, and Python APIs. We are having as well, not only safety is important, as well we need to tackle security. So we tackle safety, security, and overall everything integrated as a system. And this is extremely relevant. As I mentioned before, the shared memory communication in order to enable a high performance communication between applications in the same plane of memory. And as well, for sure, we are working on having interoperability between different DDS stacks in order to be able to cooperate in an overall environment. When we go to the certified version, and this is extremely important, so we see a continuous development between pre-development and mass production. So our goal is, in a matter of a click, you should be able to go from a pre-development environment towards a production environment. We have to freeze certain configurations, and as well, there will be certain features will not be available in the certified edition in order to be able to have that safety element out of context or to achieve a safety environment. And we'll have a C API and C++ API with end-to-end protection. So at the end, we are working to achieve an up to ASIL-D standard or ISO 26262 compliance standard. But we will, the certified edition will inherit a lot of features that we'll have in the professional edition, for example, IPC mechanism or that zero copy mechanism, as well as TSN. And this is extremely important. Our goal, as I mentioned before, is not the first time that we heard TTS in conjunction with TSN, but we have never seen it working properly and fully integrated. And our major goal is to merge those two technologies, to make it easy to work with those technologies, to make it even transparent to work with those technologies, and eventually to derive an end-to-end configuration in terms of software, and as well as in terms of networking towards the users. As I mentioned, and this is extremely relevant as well, in the area of the microprocessor, Zetta Auto is powered by DDS, and it's powered by Eclipse Cyclone DDS, which Angelo and his team, they have been working already for quite a lot of time. And as well, in our path towards the certification and our path towards having certain modifications in that stack, we are as well pulling it back to the community and putting it back in overall open source. So as well, it's extremely important for us as well to enable the community to work with the technology that we are betting on, and then to go from open source towards a certified edition or towards a professional edition, step by step. But you can go, you can download Cyclone.js and you can play with it. And if you take a look to the overall changelog, you can see that we are pulling back all the different modifications that we are doing on our way towards certification. This is about DDS, but usually automotive electronic control units are not only based on microprocessors. So microprocessors are the more heavy loaded guys with a POSIX operating system. So here DDS plays around pretty well. But then we do have the microcontroller side of things. Microcontrollers in automotive, they are having a different pace. So usually are slower, sorry, not slower, but smaller in terms of capabilities. They do integrate an AUTOSAR Classic stack. So it's is much more restricted, the overall environment. And at the end, we started thinking about, well, we cannot go only with DDS in the microprocessor. We need to enable that communication as well towards the microcontroller. And the typical use cases that customers they want to have is in the area of the microcontroller, they do not want to understand much about DDS API. They want to have it fully encapsulated with AUTOSAR Classic or AUTOSAR RTE, but still they would like to communicate with a DDS application that might reside somewhere within the vehicle in another ECU or in another SoC. It needs to run in an extremely performance manner in terms of not only execution, but as well in terms of footprint. So those devices are much more smaller, as I have mentioned, but also they need to exploit quality of services together with the other DDS stack. And at the end, we're scanning the market. Here, Angelo, you can chime in because you mentioned before there are different solutions that are out there, and now we'll let you to comment on those solutions. But what we have identified is that none of those solutions are actually fitting the bill in order to be able to have a high performance behavior. Please go ahead, Angelo.
And I think it's very important to clarify because, as you just mentioned, we are as transparent as our source code, which is open source, right? And by the way, if you look at our Cyclone's configuration, you will notice that if you really want to test the other vendor for how close or far they are for implementing the standard, you can set a strict interoperability mode, and all of a sudden you will detect all the violation of the other vendors. Okay, so that's first point. Second point, we have had several experience with customer that wanted to completely move to Cyclone DDS and remove some of other vendor DDS implementation. But this famous DDS targeting MCU, right, they are not DDS. I mean, they kind of look like DDS to people that maybe are not super familiar or very expert in DDS. But I give you a few references. First of all, look at the API, non-standard API. And by the way, when you look at DDS, look at the API because few of them have standard API. And once again, we are open, right? You find an issue with our standard compliance, just post an issue on GitHub, everyone will see it. So we are under the sun, we have nothing to hide, and that's the key value of open source. So first point, they claim they are DDS, their API aren't DDS. And there are good reasons. If you want to have DDS API on an embedded, they kind of are too fat, too heavy. Second point, wire protocol. They claim to have DDS interoperability. Well, in some cases, because once again, DDS is too big to get on those small devices, and they have DDS interoperability within their own product. Try to integrate with somebody else, it doesn't work. And we know that as a fact, okay? So my point is, watch out, because again, our source code is there. You're welcome to go, look, try. Not everyone does this. And if you look, you will see that what we are saying is a fact. It's not just some speculation. Second point, XRC. XRC, it's a pity. Why it's a pity? Because it doesn't solve the problem it was intended to solve. And those of you that have followed the standardization OMG will know which was my position back then. And this is actually one of the reasons why I decided to start off completely a new protocol, because we missed a big chance to really addressing a serious problem. And that protocol isn't DDS in spite of the name. Recall that it's a client-server protocol, okay, that doesn't support any QoS, that then needs an agent to bridge to DDS, okay? So you're going for an arbitrary protocol that doesn't even resemble DDS, okay, to a very heavyweight agent that then bridges to DDS. And the overall environment is just, I would say, baroque at best. But again, my point, we have an in-depth comparison on one of our blog. It's always good, I say, to do a couple of things. First of all, when you plan to use some software, if you can, check it out and try to build it and see your experience. Second, look at the API, how simple or hard it is to write an application. And third, if you measure performance, look at the code that they're using to measure performance and try to think if this is how you would write the code. And you will notice that in our case, it's easy to build, right? It's easy to write, and there are no surprises on the performance code, and all of our code is there. That's all I had to share, Salva. Back to you.
Great. So as we said, so in automotive, performance is key. still the vast majority of the hardware resources are highly utilized. And it's extremely important to have the performance under control in order to be able to meet those SOPs. So that's why it's not only about safety, it's not only about security, it's as well how those pieces of software they do work on those hardwares, and how do they do it in a performance manner. And this is what we are taking a look at in order to exploit all the use of that hardware and software in order to give us a proper implementation. So how does it look like in the MCU side? So we're using Zenoh Pico in the MCU side. We are integrating it in a classic AUTOSAR environment. So everything is fully abstracted via an AUTOSAR Classic API. So at the end, for AUTOSAR Classic applications, developers, it works fully transparent. So you will talk to your RTE, and under the hood, we'll have all the magic happenings, having Zenoh Pico integrated, exploiting TSN technology, and communicating with the other side of things where we do have DDS ongoing. And that one, it works as well, and it's extremely important from the tooling perspective to have it fully fledged integrated. So at the end, you have DDS on the microprocessor, you have Zenoh Pico on the microcontroller, you have classic AUTOSAR, you have an IDL on the other side. So everything shall work like magic in order to remove the hurdle towards the application developers. And this is basically what we are working on. We are proudly said that we have the first version that was delivered or was released around 2 weeks ago approximately. We are working in continued releases in the upcoming months in terms of having a much more integrated version together with TSN in order to make it much more handy towards the developer. It will come the integration with QNX. So it will go step by step, increasing in overall feature set until we'll have a full implementation and the certified by Q1 next year. So I will leave that. So here you have a little bit more, how does it look like overall Zenoh in the overall ecosystem? As we mentioned, encapsulated by classic AUTOSAR, RTE, APIs, but fully blended in the overall communication, so you can exploit all the quality of services, you can exploit TSN networking, and as we mentioned, everything needs to work on one hand side flexible when it needs to be flexible, and with predictability and deterministic behaviors once that they need to be predictable and deterministic. As well, Angelo, this is for you. If you can give us a little bit of more insights on the overall comparison between Zenoh and in particular DDS XRCE.
Yeah, so by the way, this is extracted from a blog that does a detailed analysis of these protocols and provides some additional numbers on embedded targets. And what we were measuring here, and again, we've done this with Wireshark. You have all the details on the blog that the link has been posted on the chat, but was to look at the wire overhead imposed in the key phases of the protocol, which is the handshake, so the open, and the discovery, and then the actual data transfer and the keep alive. So what you should remark here? Well, first of all, that XRC performs the worst. And here we were comparing Zenoh, DDS XRC, and QTT. By the way, I just would like to clarify something. Salva mentioned a few times Zenoh Pico. Zenoh Pico implements the Zenoh protocol. We have two implementations of the Zenoh protocol, one in Rust and one in C. The reason why we did an implementation in C is because in order to target microcontroller, although the Rust environment is maturing very quickly, we felt that for microcontroller, C was a better choice based on the current ecosystem. But the protocol is one. They are exactly the same protocol between the version implemented in Rust and version implemented in C. And the name is just to recall that there is the version that you might want to use for microcontroller. Okay, so that said, you see the big difference in opening. And again, because there is that has to do with how the discovery works in DDS and how that was exposed to XRC. Okay, so and the other important things are the size of keep alive. Keep alive are sent periodically. Periodic keep alive that is the size of one, and you see that the ratio, I mean, it's almost 50 times more than a Keep Alive. Oh, Salva, we are not seeing any more your slides. We lost your slides, Salva. And your audio. Okay. I'll keep commenting the slides. So the Keep Alive, that's sent periodically. And so if you have a Keep Alive that is 50 times bigger than a Zenoh Keep Alive, right, imagine over time, right, because that's sent how much more data you're using. And then obviously there is some additional data overhead. You can barely see the data overhead from Zenoh Pico. And the discovery difference is huge, okay? It's huge. And again, each time you start a new node, you will pay the cost of this discovery, which can be disruptive for your node. But again, the advantage in terms of reducing discovery in Zenoh are known, very known in the automotive environment also. Read the blog because there are far more information, and I think will be quite insightful. Okay, back to you.
Thank you, Angelo. And then we have a couple of things more pretty quickly because we are already going over the time. We would like to emphasize the topic of TSN. There have been so many attempts already in the past. So, and our goal is to make that happen, as I mentioned. So that should work like magic. At the end, the integration from the specification of application until that works into the embedded target, the time that is being elapsed between those two different points of time, it should be the minimum as possible. So that's why on our side, we are not working only on the endpoint. We are working as well in tooling that enable us to derive TSN configuration for the Ethernet networking. So it's not only about having a DDS and a TSN transport layer, so to say, and how all those things are working between each other. Our goal is to blend it with a tool suite that enable us to derive that configuration on the overall E network and basically to speed up the overall deployment time in that area. To finalize, I will leave it, so I will not go through each of the different oriented architectures are reality in automotive. So it's an imperative, as we mentioned before. We need to be much more flexible in automotive. So the development cycles are today still huge. OEMs are missing SOPs. And by missing SOPs, they cannot sell cars. By not selling cars, they cannot make money. And the development cycles, our goal is to reduce it to the minimum, to provide that flexibility, and to seamlessly go from prototype developments towards mass production programs, obtaining the properties that embedded systems that are running into a vehicle require: determinism, robustness, safety, security. So at the end, we want to blend all those different terms in one solution, and I'm happy to do it together with Angelo and the team. So, and we will, as we mentioned, the first launch has already been done. It's a variable. You have all the technology in GitHub, so you can go there, you can download it, you can play around, and we'll go for a version that is a professional version that it will run not only for safety critical systems, but also it can run in infotainment systems. And then we'll have the certified version by Q1 next year, and everything will work in a seamless manner, going from professional edition or from open source even to Zetta Auto and Zetta Auto certified. And that's it from my side. So thank you, everyone.
Okay, thank you, Salva. So actually, we have quite a few questions, so let me go through those. So first question from Patrick. So the question is, does Zetta Auto work with ROS2 nodes using DDS implementation from other suppliers? As an example, fast DDS, or can only use Cyclone DDS to connect with Zenoh and the Zenoh DDS bridge. Okay, so maybe I can take that. So we use Cyclone in the Zenoh DDS bridge, but as far as you use a traditional DDS implementation from another vendor, you should be within the boundaries of DDS interoperability. So there is nothing proprietary that we use to make the bridge. There are some optimization that we do in terms of zero copy just to avoid going through the stack when we have a DDS application that's Zenoh bridge on the same host, which is smart, right? But otherwise, it's interoperable with any other vendor. Just to be clear, the comment I made about interoperability concerns mostly those DDS implementation that claim to target microcontroller. Those are the implementation where they've done some cuts, some changes here and there, and have jeopardized interoperability on some important cases. That's our experience, okay? So again, interoperability is ensured with any other DDS provider. Last point, in fact, 2 points. Number one, we also have a bridge for ROS. So if you have ROS robots, or if you have done any prototype for automotive in ROS, you can have ROS and ROS2 bridged through the Zetta platform too. Okay, then there is another question from Snehil, which is asking if on slide 7, that was a slide in which you had AUTOSAR, ROS2, AUTOSAR Classic, and so on and so forth, if we have a separate implementation of ROS along with Zetta Auto. You want to take that, Salva? Because, I mean, it's...
Yeah, I can take it. So what we are taking a look at, so first of all, we have ROS2, and Angelo can comment it better in the area of robotics. In automotive, what we are seeing is that ROS2 is today being used pretty much in the area of pre-development programs, and as well to enable developers mainly to get into automotive in a known framework. So basically what we are working more towards going towards the community as well, and we have published certain papers to go towards the ROSCON this year. So first of all, what we have been working is what is the missing parts of ROS2 in the overall automotive. First of all, one of the things that we have identified is the aspect of determinism across the different areas. So this is something that we are working on. As well, another thing is the aspect of having DDS integrated into ROS2 in a performant manner. As I mentioned before, and I want to emphasize this point, performance to excel performance is extremely important for automotive. And here, what we are seeing is that in the way that ROS2 it is architected, so we are having certain penalties, and what we are doing is to take Cyclone DDS and we are hardening with ROS2. So are we doing our own ROS2? No, we are not doing it. So we are step by step, we'll put back certain parts towards the community. We would like to contribute in order to make ROS2 more, better qualified, so to say, towards automotive. And this is one of the things that together with ZettaScale, we are doing. We see ROS2 in the area of the microprocessors. We don't see today blended together with adaptive AUTOSAR. What we are seeing is 3 different sort of pathways. DDS as a standalone and having an application that is being exposed towards application developers. We have an DDS within the overall adaptive AUTOSAR ecosystem. And then we see ROS2 as a parallel track for prototyping and development. And what we want to do is to provide a ROS2 blended together with DDS and adaptive AUTOSAR, and more important one, together with MotionWise for pre-development environments.
Yeah. And again, I think it could be, you could mention that the paper that was submitted at the ROS conference actually demonstrate a deterministic executor for ROS2, which is pretty cool, okay? And that's really what you need to do real-time or hard real-time ROS2, which is pretty neat. And then as ROS2 under the hood uses DDS, again, as many of you might know, we have tight integration also between DDS and Zenoh in ROS2. So all of that, as the communication layer is the same, simplifies the integration or the experimentation in automotive context, and mixing matching pure DDS with ROS2 and potentially, depending on the mapping, AUTOSAR, because in the end, what will be on the wire is just DDS topics, right? Yeah. Okay, so there is another question from Snehil asking, so that's a reference to the last slide in which I was showing mobility. And he was asking if the mobility requires explicit registration or if it's automatic. Okay, so the mobility, there are 2 ways of dealing with mobility in our platform. It can be automatic as a result of scouting. So let me explain. In Zenoh, there is a sub-protocol, that is the scouting protocol, that is pluggable. And so if you are on a cellular network, what we would do is that whenever the physical link changes, we can detect that. And then we would change also the session with the closest router, Okay, so that would fall under the class of automatic migration. We can also do migration by administratively. Why? Because maybe if you are in a factory or if you are in a city, you might want to have, I wouldn't say operator, but more software that optimizes the distribution of devices with respect to the infrastructure. So you can imagine that there is software that gets the analytics from our infrastructure and then migrates sessions to optimize the load. That's also possible. So just to summarize, we can support automatic migration or migration by administration. And the way in which you would use migration by, why do we have migration by administration? Because we foresee either operator dealing with it or optimization software actually doing it, okay? So another question maybe for you, Salva. How do you see the Zetta Auto supporting the transition from domain-based to the zonal architecture in vehicles?
Yeah, that's a really good question. So when we talk about zonal architecture, zonal and domain, they can go together. So what we see is on a zonal architecture where it's blended together with a domain-based architecture. So we have zonal devices. That zonal devices pretty often they talk a signal-based communication together towards the endpoint. So via CAN, via any other sort of automotive protocols. And then there is a routing and conversion towards a service base or a database, so to say, towards the domain control. And what we see is that the next step is that those domain control units that will get more, they will be together. There will be a sort of a convergence into a more higher or high performance compute, so to say. So at the end, how does it work? So where do we fit in, or how does it help? Is in the area of providing end-to-end properties or end-to-end timing properties between the zonal devices towards the domain control unit. So you have to think about it like you have a sensor that it detects, or any sensor that is connected to a zonal architecture, and then that sensor sends data towards the domain control unit. And in that domain control unit, we host the software that it makes either perception layers or any sort of fusion layers or planning layers, etc., etc. So at the end, we need to really make sure that the data is reaching the destination at the proper time. And in order to do so is when we exploit TSM in order to obtain those behaviors. As I mentioned before, with the tools that we are putting on the market, what we'll be able to do is to generate the configuration of the Ethernet networking with the proper configuration in order to make sure that that data is reaching the destination at the proper time. So it's not only supporting the functional behavior, so it needs to work properly, but we are supporting overall safety cases, for example, when we are able to have that claim of end-to-end properties. And as I mentioned, it needs to be, once we are doing development, much more flexible, and then at a certain point of time, we freeze the behavior and it works in a deterministic manner. So this is how Zetta Auto is supporting the overall evolution at the EE network.
Okay, more questions are coming in, but I think we can overrun a little bit. And in any case, for those of you that have to drop, the answer will be indeed in the recording, okay? So next question from Patrick is, no, so actually we have 3 more questions, okay, no, so I need to step up. So from Gregor, the question is, to which extent TSN integration is completed, and if, it's available for evaluation?
So TSN is going to be completed. It's completed already in our first version. What we are going to do step by step is to make it much more automatized. And by automatization, what it means is to generate a configuration at the transport layer. So in order to be able to map DTS together with TSN and with the underlying network, and to be able to derive the overall TSN configuration at the Ethernet networking. So that one's going to be available in September this year. So we will have it in evaluation. So we are working already in evaluation packages that our customers can use, and actually there are already some of them using it in China in particular.
Okay, then there is another question from Patrick, which is asking if it's possible to build a setup comparable to Zetta Auto using available open source tools, and is there a guide for that? Well, I think the short answer is yes, Well, I don't know if there is I mean, there are some elements that are not open source, but the bulk is there, right? So the tools for TSN scheduling, that's not open source. But all the communication technology is there. Maybe the easiest, Patrick, if you have a question, you can reach us or TTTech on our Discord channels. But all the building blocks are there. And I would argue that if you look at our blogs, you will see how to do it on the microcontroller, how to, and starting from there, you know, how to go forward, assuming you are not using AUTOSAR, okay? Because AUTOSAR, as you know, there are no open source implementation, but for the communication layer, everything is there. Then the last point that I would like to raise is that, as you know, we do, as ZettaScale, all the software we do is open source. But we can do that because then there are customers that you know, make sure that we get funding. So I think it's also important to make sure that, you know, at some point, because without people that put all that effort behind, there is no more open source. And so I think it's important, you know, to take and give in due time. But we will be more than happy to support, and all the bulk of the elements is there. Anything you want to add, Salva? No. And by the way, there is something else far more philosophical that I would like to share concerning open source. ZettaScale is a small, innovative company. And you understand that there are, you know, it's harder and harder to be small and innovative because the mega company that there are around, they push their own technology and eventually they dominate the market, which kills completely innovation. So if we want to have innovative free software, I think it's super important, as you know, to support small innovative company. And I don't say that just because I'm the CEO and CTO of ZettaScale, but honestly, you know, innovation most of the time comes from the small. But then, you know, the level of adoption that can be pushed by the big, it's on a different scale. And so I think it's super important, especially, you know, if we consider Europe and European technology, to make sure, right, that we support a small European company that are innovative. And again, I'll stop with my pitch, and it's more, you know, about making sure that we can continue to have innovative technology, as opposed to just, you know, mega corporation that push their own platform. I don't think that would be good for anybody. There is a last comment from Ramazan. I hope that I say your name properly. He has no question, but he enjoyed the presentation. So thank you very much, Ramazan. And don't hesitate to reach out. We'll be more than happy to, you know, to discuss with you on application of our stack to railway. So don't hesitate. Any conclusive message, Salva?
No, so just this is the beginning. So we're making the proper steps, and as you mentioned, so we take the challenge of making SOA well done for the automotive market.
Indeed. And, you know, it's a lot of work, but it's fun, right? So.
Definitely fun.
Okay, cool. Thank you again, Salva. And, well, I look forward to having you soon on another webinar, okay?
Whenever you want, you know my phone number.
As far as we don't argue about jamon, right?
No, that's clear. So in Spanish,
cannot discuss Italian, about jambon.
What can go wrong, right?
But let's remain on the automotive, and we'll do great. Ale, thank you everyone for joining us. Thank you, Salva. Take care. Bye, everyone.
Thank you, everyone.
Bye.
Take care. Thank you.
Bye.
Ciao.